Later we'll have easy quiz, easy quiz. The quiz easy one about delta complex. Okay. So let me go to assignment first. This time assignments, there's something to discuss. Very interesting work that done by you guys. I already shared up. Actually, I wanted to share Hong Rui one. I should share it later. Okay. So I shared Adrian one, Lydia one, and Jingsen one. Okay. Try and read their part of their argument or read their picture. Okay. See what's really going on there. And let me comment about the solution. Okay. So for the first one, right? You are asked to show that if you give a surface of genus G, and then there's two C here, two circle here, and one circle is if you remove it, okay, you will cut this genus into half. Not sure what half is gonna just cut into two parts. But if you cut the another C prime here, then you are just opening up your torus. Okay, so prove that this genus surface here, genus G surface here, don't retreat to C, but retreat to C prime. Okay, don't retreat to C, but retreat to C prime. Okay, so the point here is if you try to cut this surface here along C, what you get is some n-gon here, some n-gon. Okay, don't know what's the n-gon there, but with a circle inside. Okay, so this circle is C, and then the rest is the two set. Okay, and then from this picture, right, you can see that this C here actually deformation retract to the one skeleton. Right, deformation retract to the one skeleton on the side there. Okay, maybe A, B, A inverse, B inverse, something like that. You list it down. Okay, so this is the inclusion map into inclusion map of C into this this new MH right here. The point here is if you have this retraction, then you will have the induced map from the retraction and the inclusion that compose to identity. Okay, so this map here should compose to identity. Okay, so what does this mean geometrically? So if you take your C, okay, you take your C, your loop here, put it into here. Okay, I put it in, and then I look at it inside C again. What is it? What do you think? What it should be? It should be just itself. This is what you expect. But the point here is, if once you put into pi 1 of MH prime here, the whole this one skeleton here is actually trivial because we got a two-cell cover in. It's actually trivial there. So it becomes trivial after you include it. So you cannot go back to your C. Does it make sense? This is the contradiction. So your contradiction will use that I star is injective, right? But then after you compose, you get 0. You don't get back your C anymore. Okay. Okay, because in this pi 1 of MH prime here, this space here, this one skeleton here, the gluing here, attaching the image of the attachment should be 0. Okay, because there's a two-cell cover, two-cell attaching around this one skeleton. And then the other thing is we can retract to C prime by, I think there's a lot of methods you guys use. Send one point near to C prime or just send it to C prime, or you send it to the torus that contain the C prime first, and then you retract to the C prime. So the point here is that if you look at this picture, what is this C here? This C here actually is contractible, but C prime is not contractible. Yeah, you see this C, right? You can is it contractible or not? You can slide through, right? Can select through, right? Can C. Can I push this C to this point here? Am I allowed to do that? Huh? Can I? Try. Let's try. So if you reach here, what happened? You go top, go bottom, right? Then here also go to the top, go to the bottom, right? And then, is it possible? Or can I select from bottom? If I select from bottom, if I select like this, and then is it possible? Base point? No, we don't want to change base. Okay, so if I don't want to change base point, maybe I contract back to one of the point here. So can I like move the bottom here? And then can I move it up? I don't know. Do you guys know what I'm drawing here? Or should I use a dotted line better? So I push the bottom part to this side here. Okay. And then I can bring them out, right? I can slide up. So I bring them up. Can I pass through this hole? Let me think. Can I pass through this hole? If I push it here a bit, can I pass through this hole or not? So maybe let's draw like this. This if this hole contractible. Seems like not. Seems like not. Seems like not. Yeah, seems like not. Okay, never mind. Okay, I thought it's contractible. But it's just deformation retract to the one skeleton. Okay, but if you look at this C prime itself, right? This C prime is actually just part of the skeleton. Just one line. Alright. Okay, just one line of the skeleton. So you can retract to, so meaning from this assignment, right? This question, right? You can retract to one side of your skeleton, but you cannot retract to like the whole skeleton. Okay. The skeleton that your two cell attached to. Okay, does it make sense? Okay. Yeah. Any questions so far? No? Okay. Next one. Very glad that a lot of you like draw this up. So this is a quotient space I3. So you imagine you have a cube here. Okay, imagine you have cube here. And then what you do is you identify each square face with the opposite side. So what do you do? So you need to understand what's this identification here. So it uses right-hand screw motion. Okay, so it defines what is right-hand screw motion. Translation by one unit in the direction perpendicular to the face with a 1/4 twist. Okay, so you go to opposite and then twist by 1/4. I think people draw it out. Maybe I can share it to you. Edit. Let's look at Adrian one. Yeah, this one. Oh, it color is a bit different, is it? Supposingly there are three color, right? Okay, so you see, so if you look at the left hand side, square here and the right hand side here. So you can see that this A here get attached to the other A on the other side. So there's a 1/4 is how many degree? 45 degree. 45 degree twist. Huh? Four color. A, B, C, D. Yeah. Okay. Yeah. Yeah. And then I think Hong Rui one turn the other direction. Is it? You turn the other direction. But in this case, still okay. Let's compute the same thing. is a 45 degree. Okay. Then this pi one of this actually is the quaternion. Is a quaternion. So quaternion is a 4-dimensional vector space, right? Quaternion is a 4-dimensional vector space. But in this case here, there's only group structure. It's not really the vector space. Okay, but the group structure can be realized by this object. Yeah. What? What do you mean? Other numbers like, oh yeah, sure. Okay, yeah. Yeah, just the basis elements. Maybe this maybe one of the model is this topological space can realize this basis element. Maybe one thing you can think about is if I want to look at the whole vector space, can I extend from this topological space or not? Yeah, I don't know, but I don't have answer. Maybe you can think about it. The next one is about mapping torus here. So if you look at the mapping torus here, it's a map from x to itself. Okay, but what you do is you take your x and then cross with one interval, and then look at the image of you identify x with fx. Identify x with fx. Okay. You identify f with fx. If this f is not surjective, then it could be something that you don't get identified, right? If it's not surjective. Okay. But if it is surjective, then this is what Jingsen draw. Wait, is surjective, then this is what Jingsen draw here. Okay, you can imagine something like this. Okay, S1 wedge X1. For the case of X1 wedge S1, and then you form a cross product with a unit interval, and then you identify them. Okay. So you get the two cell coming from the product set. Then you get the two cell coming from the product set. And then the rest, I think, are quite similar. Okay. This is about mapping torus. Because in class, we talk about mapping cylinder, right? This is mapping torus. So something get identified at the end, both ends. And the last part, I think last part is interesting or not. Last part is quite interesting, this part here. Okay. So it asks you to construct a simply connected covering space of X that's a union of a sphere and a diameter. I think this one is a question that we met on our quiz, right? We have a sphere and then we have a diameter here. And then what's the simply connected covering space here? So this is basically the take the universal cover for S1 and then turn the integer into a sphere. Okay, because if you walk on this sphere with line in diameter, right? Either you walk on line or either you walk on the sphere. Either you walk on the line, either you walk on the sphere, like that. Make sense? Okay. And then the next one is union of the sphere intersecting it in 2 points. Do you have problem understanding this question or not? How is it a sphere with a circle intersecting in 2 points? Okay, maybe you can draw like number 1. Okay, anyone thought of number 2 or maybe thought of number 3? For number 2, they intersect 1 point, right? But for number 3, it's not a circle. But for the case of a union of sphere with circle intersect with 2 points, this is actually the universal cover of x1 wedge x1 by replacing every intersection with a sphere. Okay. Yeah. So it's like a universal cover of x1 wedge x1 covered with a sphere. Is it true or not? So if you walk on this circle, right? So let's draw this. So if you walk on this circle, sorry, sphere, and this circle here. So either you walk up or walk down, right? So you walk to one side. Okay, maybe you can start with the sphere, right? And then you walk on one side, and then maybe you go to the other sphere. Okay, but not that. You can also walk the other way around, right? You can walk to the other side. Okay, and then you will meet another sphere again. Okay. Yeah, and then you extend this in 2 ways. Is this right? So you walk around. So in the one side here, you should have either in and out, right? Either in and out. And then did I miss anything? So for the rest, you also need to add in and out. But this is not R2 yet, huh? How do I extend to R2? Let me think. Should I extend to R2 here? Not R2 yet, huh? So what's wrong here? Let's think about it. So, so I think you should also have on the other side, you should grow this thing, right? Because there's 2 base point you can pick when you're going up. And then from here, I think you can extend to R2 already. Because on all these, you also have to go in, go out, 2 sides. Okay? Does it make sense? Does it make sense? Yeah, Yi Heng. Listen. Listen. Later you say no time. Try ask question in class. If cannot understand, you should ask. Otherwise, you cannot figure out, then how? Okay. But if for the other case, for this number 2 and number 3, what are their universal cover? Do you have any idea? If I change to these 2 questions here. Number 2 and number 3. If I change to these 2 questions, can you imagine what's the universal cover for them? Huh? 3, no, they are all different actually. I mean, maybe after deformation retreat, they are the same. But you can draw a not, I mean, they are homotopy equivalent, but I draw it slightly different. Let's draw 2. What is 2? So the universal cover for S2 actually is X2 itself. And then for circle is R. So actually, you can draw this as like this. So for number 2, right? You can draw it like this. There's a line that wedge with bunch of S2. Maybe I draw it like this. It's easier to see. And then how about the other case? The other case is actually similar to this case here. Okay, but what we're gonna do is instead of wedge at one point, wedge at 2 point. So see, so I think it's like this. Actually similar to number 2. Is it true? Can you check? Hmm? Yeah, yeah, yeah. And it should be the same, right? Because the one diameter is inside, one is outside only. Should be the same. Yeah, should be the same. Okay. Yeah. So if you interpret as these spaces, then it's wrong. Okay, so it's really union of a sphere with a circle intersect in 2 points. Okay, so this is about this. And then the last one here. Okay, the last one here, yeah. It's true that I didn't tell you how to prove didn't do in class, do in front of you, how to show that this normal subgroup is actually the normal subgroup we consider. But I include one example actually I missed on that discussion. And also I put up this tutorial here. Maybe I mentioned to you, but I didn't say that you are actually using it. I think in the tutorial 3 here. I think I mentioned this in class as well. If you still remember that how we decide what are the generator for a connected graph. If you still remember on the bounded complementary region, not sure you remember or not. But it's true that we didn't really spend time doing that. So if you try to solve it in any sensible way, I will just give my. I think someone tried to prove using quite a few. Maybe you want to prove using that transformation, but I feel like not complete yet. Maybe you can try and argue with me if it makes sense. Where is it? Maybe I want to stress the importance of this question. Let me find it. Tutorial 4. Yeah, tutorial 4, this one. Actually, you can use tutorial 4. This question. Yeah. So if you have a connected graph, okay, so in our case, it's like that, with a finite union of straight line, then pi1x is free with the spaces of loops formed by the boundary of the bounded complementary region X here. Okay. Yeah. So what does this mean, huh? So this means that if once you get this picture, where is it? Oh, I didn't draw this picture. Maybe let's borrow some picture here, huh? Yeah. 看一下金色有没有 Yeah, 金色也是有，想看这个。Okay, so if you have this picture here, so how many bounded complementary region here? So there's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 like that. Okay, and then you argue that they are conjugate to some generator. Okay. I think only one write it down properly. Yeah, that is Adrian. Yeah. Yeah. Okay. Yeah. Any questions so far? Any questions so far? Hmm. Hmm. Is the correct one? How do you show that? Huh? So either you use what I said just now, or either let me see. I think this is similar, but yeah, just show that the rest of the generator actually is generated by these generators. Okay, because you want to ask about normal subgroup, right? Normal subgroup is closed under conjugation. Yeah. So you can throw away those that come from conjugation. Okay. Did I ask you to prove this is normal? Because you want to show that it's a normal subgroup generated by this thing. Okay, so you use a group of depth transformation to see that that is the normal covering space, and then you want to prove that actually that's the normal subgroup correspond to that covering space. Yeah, I think most of you didn't do well in this part, last part, because I didn't spend time doing it. Yeah, so this is something that I want to pass through. I mean, in this kind of system, if teacher didn't spend time, can you still do it or not? Not everyone, so because this is also a main, I would say, excuse given by the educator that we need to do everything. So I mean, I think one of the main difference that principle that I opt for is I want you to like build your own stuff. I want you to build your own stuff. It's not like build my stuff. My stuff is already being built. Why you still want to build my stuff? I want you to build your own stuff. So I teach you some basic thing to understand something. Maybe you need to take a leap. Okay, so we will try to adjust and see what kind of leap you need to make such that it is not too big or too small. Okay. Jinsen said this is the coolest assignment I've ever do before. 因为很多照片还是这样。哦，还有那年女生，OK。啊，有东西被粘起来，OK，很好，很好，非常好。哦，OK，很好，很好，很好。Yeah, this is the point of it 所以你觉得这个很好写，就是为什么这个 field 会发展的原因也是这样。为什么它会发展？就是它很自然，它有一个自然，有人觉得很自然。如果不是全部人，但至少有人有觉得很自然。Yeah, OK，对不对？OK，很好，Good。So, yeah，差不多就是这样。Assignment。I think assignment one 没有什么好讨论吧，很正常嘛。assignment one，如果你有问题的话可以问。assignment two 比较有意思一点。Okay, let's continue from Monday. Let's continue from Monday. Okay, so let's continue from Monday. So do you remember the important thing that we deduced on Monday or not? So if X is half connected, then H0 of X is just Z. Okay. So H0 kind of count how many path connected components, because we also proved that H0 X actually is a direct sum of H0 of path connected component, and then all these are set. Okay. So if you know that your space is path connected, or if it is not path connected, you can split them into path connected space first, component first, and then you direct sum them. So actually you are really counting how many path connected component for your H0. Okay, this is very similar for your homology zero cohomology. So you're counting something very basic. I think it's a function that define on the whole space. You count how many possible function is that. And then, so how do we prove this? Basically, we need to establish that. So we want to show that H naught, which is equal to C0x over E mesh of delta 1 is isomorphic to Z. Okay, so if it is from group theory, right? If it is group theory, then you would have to make a map from the quotient space to Z. Okay, and then this is what we think about as a negative simplex, -1 simplex, because it's a map from 0 out. Yeah, prove this.
最后
Yeah, 最后we form the 1 simplex, right? Using the 0 simplex that coming from the kernel. Oh, okay. What's this map? Okay, let's recall what this map is. So you have a chain in 0 chain. Okay, you map it across. You just take the sum of your coefficient. Okay, so if it's in the kernel, then that means that if it is in the kernel, this means that this thing has to be 0. Okay, you want to show that the kernel of this map here, maybe call it D0. Kernel of D0 is equal to the image of delta. Okay, so how do we prove this? How do we prove this is we pick a base point. Okay, we pick a base point in X. Okay, we pick a base point in X. Okay, X naught. A. Yeah, we call it a base point in X. Right. So we got an X naught here. And then we apply, suppose, okay, let's suppose first. So suppose, so one direction is easy, the other direction is hard. So let's do the hard one. So kernel is in the image. This one is hard. Image is in the kernel is easy, just direct computation. So the hard one, what do? You suppose that there's a 0 chain inside your kernel. Okay? And then this implies that the sum of ni is 0. Okay. So what you do is you want to show that there exists a one chain tau such that boundary 1 of tau is equal to this corner here. Okay, this is what you want to show. Want to find this tau. Okay, so how to find this tau here? So to find this tau, what you do is I take an S naught and then I look at what's the image of sigma I on this S naught. Can I do that? Can I do that or not? What are these sigma I? These are the 0 simplex. So what does 0 simplex do? 0 simplex is a map from a vertex, a point, from a point to your space. Okay, so I take a point, I let the sigma 1 to sigma I to act on it. It's a point in X. Okay, and then because this is path connected, right? Then I can look at the path that join X naught to this sigma I X naught. And then I call this tau I. Make sense? Okay, is it okay? Tau I. Yeah, tau 1, tau 2, sorry. Tau 1, tau 2, tau 3, and so on. Until tau I. Okay. And then I take the same linear combination that this sigma I has. Okay, because it will work. So I just make it work. So I just consider tau to be sum of I1. So sum of I, don't know where to stop, and I tau I. Okay. So if you restrict the sigma 1 to tau, right? Sorry, apply sigma 1, sorry, apply partial 1 to tau, what do you get? You are taking the endpoint minus the starting point. So let's say V0, V1, right? So if you throw away V0, you are +1, is it? And then if you throw away V1, you get a minus. Let's check out. Okay. But what's your starting point for all these tau I here? The starting point is S0. Okay, the starting point is S0. So this is your ending point. So what's ending point here? What's ending point here? Okay, maybe we deal with it later lah. So starting point is just NIX0. Okay, and then ending point. Ending point is sigma I exactly. Sigma I. Okay, sigma I is your ending point. Correct or not? Or if you like sigma I S0 like that. Can I do that? Can't really do that, right? I can't really do that. It's just a restriction map here. It's just a restriction map. Yeah, it's just a restriction map. So I cannot really write down the image. Maybe one thing that maybe confuse you is these are map, not image. But the point here is, what? The point here is this all start at the same place. So this is actually equal to some, let's call it sigma 0. They are the same map. Okay, so what I want to say here is Ti on V0, V1 hat is equal to Tj restrict to, these are all restriction, restrict to V0, V1 hat for I not equal to j. They all start at the same place. I mean the same map, same map. They are the same map. Okay? But for the ending point is a different map, and then they correspond to sigma I. Okay, so in the end, in this case here, we can actually factorize the sum of ni from this ending map here. Okay, so sigma I. So let's call this sigma I as all these things. Okay, so that you will get sum of ni sigma I minus 0 because it's in the kernel. This sum is 0, so you get sum of ni sigma I. Okay, does it make sense or not? Okay, maybe there's a confusion place. Is they are map, not image. But obviously, the map will be determined by where they send the thing. Okay, question. Question. 啊，又要去那边了。Okay. Okay, so far. Okay. All right. Next. Okay, next we will introduce something called the reduced homology here. Yeah, maybe let's use slide first. Yes, yes. Which one? What? Oh, reduce. Yeah, yeah. Okay, let me introduce first. I haven't introduced. Okay, so let's introduce a reduced singular homology. So the motivation here is we want to produce a homology such that the homology of a point will have trivial homology group in all dimensions, including 0. Because if you still remember, right, a point obviously is path connected. So H0 must be Z. So we're going to produce one kind of homology that's it will become just 0 chain for a point, for the homology of a point. Okay. Point, just point. One point set. Okay, 1 point set. 1 point space. So what we're gonna do here, we reduce this is we actually add in the augmentation homomorphism, okay, as our d delta zero. Okay, usually we don't have delta zero. Okay, because delta zero will map into negative dimension, but we don't have negative simplex. So we won't care about negative part. But now we add in the extra negative one part, which is z, just z. Okay, just for z. And then this will change things. Okay, here, okay, there's some remark here. We will require the x is not empty, otherwise this z will appear in the negative dimension. Okay, so you will have non-trivial things in the negative part if everything else is zero. Okay, so we better require that x is non-empty. Second is how to think about this extra map here. Huh? Because if it's empty, then other than -1, they are all zero. There's no map. So you were left with 0, 0, 0, z, and then 0, 0, 0, 0. So the kernel of z going out is z. There's no image coming in, so it's z. Z survive here. Z will survive. There's no image coming in. Yeah. Okay. Okay. Everyone okay or not? This is a simple chain calculation. Yeah. Yeah, epsilon is subjective. Yeah. 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 Okay. And then how to think about this z? Because for the rest, you will think of a map going from the n simplex to x, right? Then what's the negative simplex to x? Okay, what's the negative simplex here? So you could imagine that that negative simplex is something built up by empty set, which we call the empty simplex. Okay, and then the augmentation map is just remove the vertex. Because in C0, you got one vertex, right? So remove it. If you want to put into the same formalism, you can do this way. Okay? Question? A question? Okay. If not, then there's one proposition here. Maybe we can spend time proving this and then we can take a break. Yeah. So let's prove this. So this proposition is what happened is hash naught of x is isomorphic to hash naught tilde x plus z. Okay. So how about for the rest of the n? What is hash naught tilde x? Okay. So the hash hash n tilde x. So hash n tilde x is just defined to be the homology of the chain group that we had just now. So that chain group is the previous chain group plus -1, non-trivial -1. For the rest, is still the same chain group you get from the normal homology. So they should be the same. Not isomorphic, and I think should be just the same. Because the map didn't change. Okay, so if you look at this map here, the map here didn't change. No change here. Okay, just that I add something extra at the 0 degree. Okay, after 0 degree, I add something extra. For the rest, no change. Okay, for the rest, there's no change. Okay, so we want to deal with this 0 degree here. -1 here, everyone okay? It's 0. Because this map is surjective. Last time we showed it. So surjective mean what then? Let me think. So kernel is z, image is everything. So z over z is 0. Okay. Yes. Maybe for that part we need isomorphism for the hash -1 part. So maybe we need this for hash -1 part. Yeah. We show that what? Yeah. Trivial. Wait, so wait. So what you trying to do? You want to prove now? You want to prove? Want to prove here? Try and show. Hmm. So what is h to the x here? Yeah. I mean, in the case just now, obviously, if this proposition is true, then it should be trivial. But now we want to prove this true for all x, right? We want to prove this is true for all x. In the previous case, obviously, if this is true, then it implies that the reduced homology is zero, right? So the point here is this is defined to be kernel of epsilon over image of I. Okay. Then how do we show this? One way to show this is can you show that hash not x, okay, quotient out by hash not tilde x is z. Can we do this? Okay, can we do this or not? If we can do this, then it will split into direct sum. Last time we split into semi-direct product is because the image here, the core domain here might not be normal inside the original space. Okay, we can split into direct sum if these two are normal here. But obviously kernel must be normal. So Z should be normal everywhere. Okay. So can we show this or not? If we can show this, this will implies h naught x is isomorphic to Z plus h naught tilde x. Okay, so meaning we want the map from the homology h naught x to Z to Z. Right. How should we do this? How should we do this? Maybe start with what we know. Start with what we know first. So start with what we know. So start with what we know. We know that there's a map from C naught x to Z by this epsilon. And then we also saw from last proposition that h naught x is isomorphic to C naught x portion out by image of del I. So there's a commutative diagram like that. And I think by first isomorphism theorem, we have this map. Let's call it epsilon bar. What's wrong with it?
Because you just pick 0 to 0 to portion. Why do you?
It fits into this diagram. It fits into this diagram. I mean, you can put this away, right? It fits into this diagram. This is the quotient property of this. Correct? I just call it a new name. Okay, if you don't like this isomorphic, I put equal sign. Okay. Then what? Then what should we do next? So h tilde s naught is a further quotient. Is a further quotient. So can we do anything here? Can we do anything here? Is this an isomorphism? Is the epsilon bar an isomorphism? Huh?
Of the X layer.
Yeah, true. True. So in this case here, epsilon bar here, how to exist? Does it always exist? Okay, maybe I cannot use first isomorphism theorem, right? Otherwise, it will be isomorphic. So is this exist or not? Maybe not first isomorphism theorem, but this map exists or not? For this part, for this map to exist, right? What is the property you need to take? So you already know how to send S not X already. Then what's this quotient here? This quotient means what? This quotient here, the thing have to go. This after quotient, everything in the denominator should be 0. So you should send 0 to 0. Okay. So is the thing in below going to 0 under this map here? So this might not be isomorphic, huh? Might not be. Okay, so we cannot use first isomorphism. Might not be. Might not be if S is not path connected. But we want to build a map here. There will always be a map here. Okay, why? Might not be isomorphic if this is true, but there exists such map since epsilon on del 1 is 0. Okay. So everything in the image of del 1, right, is going to send to 0 under this epsilon map here. So you have a well-defined map. To be well-defined, you need to send the thing in 0 to 0 as well. But everything that's the image of del 1 is going to send to 0. Okay, there's a map here. So this map is again surjective. Huh? Sorry? Yeah, mapping property, yes. Yes. Mapping property, not the first isomorphism. Okay, that's the mapping property. But then we can further quotient, right? We can further quotient it to get a real first isomorphism theorem. So we can further quotient it. So we build another ladder up. So H naught X quotient by this kernel of epsilon bar. And then build go up to Z. We will take this be the isomorphism. Okay. So the question here is kernel of epsilon bar here H tilde S or not? Is it true? Okay, so the question here is kernel of epsilon bar here equals to H naught tilde X. Is this true or not? Okay, if this is true, then this is what we want. Okay. So let's think about it. So is this true or not? Maybe I draw in the same picture so that you can keep seeing this picture. So, but H naught tilde X, what is it? It is by definition kernel of epsilon over image of del 1. So is this equals to the kernel of epsilon bar? That's true. 会不会看久了就变 true？不会，不会啊，当然，他们是自己骗自己。解释一下为什么 true？解释一下为什么 true？不过看久有一个好处， 你可能会看出一点什么东西来，你不看的你就没有，但是你不可以说你看久了它就对。Okay, so what is it? Okay, so kernel of epsilon bar. So what's the kernel of epsilon bar? So where's the epsilon bar come from? So the epsilon bar come from epsilon. Okay, so anything that sent to 0 by epsilon, definitely this epsilon bar have to send to 0. But the domain of epsilon bar is what? C naught x quotient by image of delta I. Obviously, you need to identify the element in the kernel of epsilon based on the identification you make on image delta I. Okay or not? Does it make sense? Question? Okay. So what is epsilon bar? So you need to understand what is epsilon bar first. This epsilon bar comes from epsilon. Okay, so how to come from epsilon? The problem is first you follow this diagram. This is a commutative diagram. So meaning what you do first? You quotient out your C naught by image of del I. So meaning what? If their difference is by image of del I, they are the same. Or another thing is you equate 0 with image of del I. Okay, so 0 will go to 0. Image of del I also go to 0. Okay, yeah, okay. 哦什么？哦什么？那你解释。没有，你解释也是可以。嗯。
Each of delta one is in the kernel of epsilon objects. And what we use is that whenever we want to send in H0x to 0 should be itself in C0 should send. I think my understanding is that the element in per epsilon bar should be a closed set of elements in per epsilon.
Yeah, that's what I written down. Yeah, so the point here is why you understand as a coset, because epsilon bar is already acting on coset. Yeah. So yeah. So because kernel of x. So kernel of epsilon is coming from C naught x. Okay. Then kernel of epsilon bar is coming from C naught x mod out by image of delta. Okay. So the kernel of epsilon bar have to be coset. Okay, coset quotient by image of delta 1. But why is it just kernel of epsilon? Is this easy to see? Obviously, kernel of epsilon over image of delta 1 should be living inside here, because already get sent to 0, after quotient should go to 0 as well. 不然间又变正诶，10的东西应该会模起来了。OK， 啊，也是这样可以。OK， 下次我们要做一个即时实例。可以模起来。Okay, how about the other direction then? Maybe the other direction needs some explanation. Why kernel of this del epsilon bar here can be written in this coset form? Okay, so meaning if it is get sent to 0 by epsilon bar, why is it coming from? Maybe this part needs some explanation. If you are still confused, I think this part is a bit harder. Always this part is harder actually. Always is this part. You just know that the sum coset gets sent to 0 why is it coming from the 0%? 我想现在可能去越来越多 age 是 yeah, I mean, I think this has to do with our definition. Okay, 那我们解决完这个，我们就 take a break. Okay, so suppose 那我们解决完这个，suppose n is in the kernel of epsilon bar, then 我就可以 write n to be sigma plus something in the image, maybe sigma plus I, okay, such that sigma is in C naught X, and then I is in the image of del I. Okay. Then suppose sigma is not in the kernel of epsilon. What could happen? 哦，还是不要这样 prove 了。I mean，我们就 direct proof 就好，不要搞这样多花样。Okay, so we just apply sigma bar on n. We know that its kernel is 0. And then on the other side, sigma bar on this. What is the definition of this? Sigma bar on this sigma and plus I is actually equal to sigma. 这么叫 sigma？ 这个叫什么名 ？Epsilon. Okay, epsilon sigma plus epsilon I. But epsilon I is 0. So epsilon sigma have to be 0 as well. Okay, 非常好啊。Can we put this into AA1 assignment? Okay? Yeah, okay or not? 还有问题吗？没问题。Okay. Let's take a break. Let's break for 5 minutes. Huh? Okay. 3:10. We come back.
Force in my mouth, or rather, you don't put force in my mouth.
你还是我？
应该是我，我只是表示一下你的话。
哦。他有讲，他不要讲吧？讲掉。
为啥我们学校的老师都那么佛系？
HT 的哪一个是 HT 的？HT 的是那个 homology of 这个情况，还是普通的？还是没有这个？HT 它是有这个的，但是有跟没有的差别也是在这个位置吧？对哦，在其他位置是一样。是吗？倒数吧。哎，一恒你有改吗？后来我给你的那个 version 还没有改完，还是有改？有改，还没有改，还是还没有改完？还没有改啊？还没有改完，还是还没有改？你有改一点的话，你可以跟他 update 一下。但是你改完了，你再 send 我一份呢，我就 update 在 mood 的。So try to be as update as possible before midterm, and then 之后 midterm 你还是要 update。
这个的 kernel 是整个诶，
他说他的运很穷，没有钱付我们上学期帮他打一季的啊，是吗？
可以做这个
H0 是 kernel D0除一变成 D1
啊，
H0x 就是 C0 portion 叫 image of delta
就
one，
是 C0。
因为你本来那个 chain 是把它送到零的，它的 image 不就是全部？你要把所有的东西，
对，我看错 chain 了，
不是那个 chain 啊，是
这个要变成零。
对，是原来那个 chain，现在我给它
原本
加了一个。
啊，对，这两个圈是不一样，这两条圈不一样。
设上去，这不是 subjective 的咩？
哪一个
问题啊？
哦，应该要 subject 这个啊，这个 subjective 是上次 prove 过了，这个 subjective 的话应该要从这里来。
嗯，哎，我想问，为
嗯，
啥我们看的东西好像全部都是一个 topology 个 space 的，然后再给它去看它上面的类似于 data complex 的东西？
哼，
我们能不能看就是随便一个群，然后它里面的东西不一定跟一个 topology 个 space 有关？
比如说，
不知道就我们看 chain 的时候，能不能看就随便一个 chain of，也许一个 group homomorphism，然后
可以啊，这个就是 homological algebra。然后我们就是想要打算从这里再 build 回 topological space，就是任意啊，能不能再 build 出一个 topological space？
哦，
现在是从一个 topology build 出这些全 complex 嘛？那我们 homological algebra 就是会想说，如果我随便放这些 module，然后这些 differential 在，我能不能 build 回一些 topological space 哦？我可不可以放，比如说我们可不可以放epsilon delta 在这些圈 complex 上面？然后你可以想象哦，我们可以用 morphism 去量这个距离，什么样的 morphism 去量这个距离呢？这有其他的解释
我学到的这些东西，
不可能，这是很最浅显的，这是最浅显的东西。那些东西它没有解决，我们才刚刚把 metric 放上去吧，而且也不是随便的圈 complex，那个圈 complex 还要符合其他三角形的条件，所以又有 triangle 出现在那边。
你们是谁？
I mean 我学校的一个老师，就是他拿了很多钱去到欧洲啊，2 million 的 euro 吧，欧元2 million 还是2 million 来着？
这样多，
也很多，他直接退休过去做了。
你这个 isomorphic 能用的？
这个 isomorphic，这个 isomorphic 是因为我已经把这个可能切掉了，因为这一个的问题是它不一定是它的可能，如果是 pub connector 的话，这个就是它的可能啊，but 不一定 pub connector 就是你可能还没有切完你的东西，你还要再多切一点，多切一点就是这个。
这一个三角形，
对，
把这个 kernel 切掉，所以这个就直接变成个 isomorphism 就完了，其实。
对，
但是这里我们它是 subjective，只是我们切掉的东西不一定是它的 kernel。
对，
所以这个我也不知道是什么东西，所以要重新看过这里的可能是要切多一次。
嗯
有，
嗯
我这
因为你只切你只切可能的一部分吧，你还没有把整个可能给你切掉，你只是切掉可能里面的一部分吧。
它一定你喜欢 D 吗？
对啊，这个是全 complex 啊，或者是你要算一算它，因为你有一个头一个尾嘛，那你一定有一跟减一嘛，因为 delta one 是从 one simplex 过来的，所以 one simplex map 下来过后有一头一尾，一头一尾就是一个加一个减嘛，所以加减肯定是零。
不是前面有讲过了，
前面有讲过吗？很奇
来咯，delta
先
E
讲过
是一个点，
我在 proof 那个时候有讲过，糟糕，好像有 skip 掉。 I mean 我有给有类似的，有，但在 show image of LE 是在可能 exception 的时候也看到这个。
对调意思。
Okay, or not? Shall we start? Okay, so something to note from the proposition just now. This H0 and H0 tilde, right? They are considering different chain complex, and then the difference is just happening at the -1 part. So H0, the -1 part is 0, and then H0 tilde, the -1 part of your chain complex is Z. This is the difference. 啊？什么？给什么 ？Z 没有放去零啊，那有送去零
原来那条群是你加了一下，有一条新的群。
啊，就是我们 define 的，我们 define 的。
那条新的群。
因为之前的 definition 是没有 negative 的 simplex 嘛，现在我只是 artificially add 一个Z 上去，然后 turns out that 有一些 meaning 在，然后有一点好处。好处就是把 homology of point 变成 zero chain complex. And then yeah, so the point here is because if X is not path connected, then the kernel of epsilon might not be image of delta one. So meaning H of 0x 还没有切够，还切不够 because image of delta one is inside the kernel of epsilon. 所以你还没有切完 the kernel of epsilon. 所以你继续切。切完过后就是我们所谓的reduce sum zero reduce sum， 对了，切不够，还没有这个 isomorphism 在，所以我要继续切，把整个kernel给它切掉。But then this whole kernel here will need to be identified under image of del I because we are considering whole set. Okay, good. Yeah. Okay, next is about the homotopy invariant. So meaning we want to show that that's the goal that we want to show last time, that we cannot do it for simply sheer homology because otherwise too tedious. But for this is already quite tedious. Okay, we want to show that homology equivalent spaces will have isomorphic singular homology. So how to do this? First, we will show that every continuous map between a topological space will induce a homomorphism on homology. Okay, and then we show that this induced homomorphism here is an isomorphism if F is homotopy equivalent. So here actually there's some very genuine idea. This involves some very new idea, genuine idea. Okay, that you never see before. Okay. So first thing is induced map. Again, we will say that singular homology is functorial. So what does this mean here? Later on, we will introduce more categorical language after we see more property. But for now, let's introduce this functorial meaning first. So what functorial means? All the rest below is mean functorial. Everything below is what functorial means. So if it is something is functorial, then this is what it means. Okay, it means that if you have a map. Okay, so maybe this word doesn't suggest any didn't shed you some light on this functoriality. So maybe let's label this singular homology first. So let's label it so that you know what is changing, what's the variable, okay, what's the function. So the function in category theory is functor, it's not function. Why? Because in category, the function need to tell you where the object go and where the morphism go. So it becomes a functor, not a function anymore. Because function only one input, but the function in category theory, you need to tell me where the object go, where the morphism go as well. Okay, so let's see why is it a functor here. So singular homology is look like this, Hx, or rather Hnx. Maybe I put a dot here because there's a lot of n here. So this means if I have a map in between x, meaning topological space x and y, I need to tell you what's the map in between h dot x and h dot y. Okay, so let me draw here. So a map from X to Y would imply a map from so what's the notation I gave here? Let me see. Okay, it's me. Okay, so F star of Hn Hx to Hyx. Okay, but in between the area, we actually need to pass through one thing first. Before go to homology, right? We need to pass through the chain complex first. Okay, actually there's an intermediate step happening here. Actually, secretly we have two functors, but later on we will describe this. Huh? But actually you need to pass by the chain complex first. Okay, so actually you need to pass by the chain complex. So let's denote it as a Cx and a Cy. Okay, and then we'll use F sharp. Okay. Okay, so we have a continuous map on X and Y, and then we go to this induced map on chain complex, and then chain complex to homology. Can you imagine what's the transition from chain complex to homology? What's the transition here? What's the transition here? Chain complex to homology. Homology defined by what? Kernel over image. Okay, so you need to show something well defined there. Okay, something has to be well defined there. And then is it clear that a map between X and Y induces a map between chain group? Is it clear from here? What's the definition of this chain group? It's some singular simplex, right? So delta n to X, and then one side is delta n to Y. But you have a map from X to Y. So you can transfer all the singular simplex on X to a single simplex on every level. Compose. And then the next step, check well defined. This is the work you need to do. Okay, no? Extend is easy, but well defined you need to. Okay, so to check well defined, what do you need to do actually? To check well defined. Oh, before that, is this very familiar? Checking on composition and then checking on identity map. Familiar or not? I think we saw this on the fundamental group, right? So we can say that pi 1 X is also functorial, actually. Okay, so I think this non-trivial thing is to check it is check it is well defined. Let's see, how should we start this? Okay, how do you check well-definedness? What do you think you should check for well-definedness? How should I put this? Well-defined. So well-defined actually occur at hash X, right? So the kernel of your n level of X should go to the n level of Y, also serve as a kernel. And then image, the boundary from the X part also need to go to the either kernel or the boundary of the next part. Okay, so that is well defined. Okay, so let's see. Okay, so one very important thing to establish is, let me see first, is this one. Okay, so this is what we claim. Okay, so have I tell you what is F sharp? I tell you what is F sharp, right? It's the map that defined on your chain complex. And then this is what, yeah. What's the map between what? I thought I already explained. You just compose, right? What do you mean?
Ladder.
What ladder? I cannot imagine. Like a ladder. What ladder you want to see? Oh, you want to ask about whether this commute or not? Yeah, this is what we're going to show. we want to show this. Okay, we want to show this commute. Okay, so I tell you how to build this F sharp, right? You just compose F with the singular simplex from X. Then now I want to show that this commute. Once this commute, this will show the well-definedness on the homology. Okay, so two things to do. One is to show this diagonal commute. Second thing is to show that this commutativity gives you the well-definedness on homology. Very special, huh? Okay, something commute and then you have a map on homology. Okay, so why this commute? Let's check. I wrote it down already. So let's do on one side, do F sharp delta sigma first. But delta sigma is what you just throw one vertex away and then with the alternating sign. But F is what is F? F is linear, right? So you can bring the F in and then F composed with the sigma here. But then what is this? We claim that this is just F sharp. It's hard to see or not? This is F sharp. So you do sigma and then you do F. This is how we define F sharp, right? Okay, basically what we do was we apply yeah. Should I write down what is the definition of F sharp? Or you happy or not? Or you're not happy? If you're not happy, let me write it down first. So F sharp is going from Cn to Cn plus 1 to Cn x. Sorry. So just Cn to Cn. So this F sharp is defined for every level, right? Let's give it n labeling here. So what we do was we have a sigma on one side and then we send it to do sigma first and then do F. That's it. Okay, so maybe you think that I skip step here, huh? Okay, so to make sure that I don't skip step, I just add one more step here. So what's the step I'm gonna add here? Exactly, I want to add this step. So it's F on this whole thing here. Okay. And then I just pull the scalar out. Okay, because this is just the definition of, I think, scalar product. Yeah, scalar and then sum. Sum of your function. Definition of sum of function. Does it make sense? Does it make sense? Or you don't know what am I talking about? How about like this? Fgx plus hx. What is this? What is this? F of gx plus hx. Shouldn't it just be fgx plus f hx? This is the definition, right? This is the definition. Okay, I just split it up. Okay, so the commutativity here is just apply the definition of function. Okay. Anything to add here? Comment. Okay, so maybe one more comment is this F sharp is come with n. So the label maybe is important for later. So for example, this F sharp inside here is n plus 1. The F sharp outside is Fn. Okay, so maybe it's important for you. And D, the first D is delta n plus 1. The second one is delta n. Yeah, exactly. Yeah, exactly. So if you see that the bottom here, we don't label here because actually their formula is the same. So that's why we don't really care at which level. Okay. But because in this field, whenever people write this commutative property, right, they will already know they will differ by 1 to x. So that's why we skip it. If you don't want to skip it, you just write it like that, write properly. Otherwise, you can just remove it. Okay. For now, question. More question. If you have answer, yeah. Topological space, chain complex, and then from topological category of chain complex to category of homology.
Right.
Okay. Actually, it's module, not homology. It's module. So what's the use of this commutativity? So if you compute this, if you say start from let's see where to start here. Okay, let's start from here. Okay, take an alpha such that boundary of alpha is 0. So meaning it's in the kernel of this level of delta. I don't know where is it. Just call it an n level. Then if you do what do you do here? If you apply f sharp to this alpha here, okay, if you apply f sharp to alpha here, and then do the delta again, so what is it? Okay, so this two delta is the same. Okay, so for beginner, right, maybe I label for you. This is delta and this delta. Okay, so f sharp delta, what is happening here? F sharp delta here, we send this n simplex here go to the from n simplex of x go to the n simplex of y, and then I do okay. Maybe there's some more I need to label here. Maybe this first delta is coming from x, the second one coming from y. Kind of not. Okay, so I take the kernel. Okay, I take the kernel, the whole cycle, okay, in x, I send it to y, then I do the boundary at y from the differential map. But it commute, right? Okay, I can commute it back to the x1. And I can commute it back to the x1. Okay, and then but we know that it is 0 in this case. So what? So this evaluate to 0. Okay, so what this means is you send the cycle in x to the cycle in y under this map. So you send something inside the kernel to something inside the kernel because homology is kernel over image, right? So you send something in kernel to something in kernel. Something of kernel in x to something kernel in y. Okay, and then also from this commutativity, you can see that f sharp also bring boundary to boundary. Okay, so what this means here? So let f sharp map on the boundary, but it commutes, right? Then it means that this element here will be a boundary of something else. Okay. Then this will induce a homology on induce a homomorphism on homology here. So maybe I shall write this down. This kernel of delta n of x over image of delta n plus 1 x. And then on the other side, we got kernel of delta y n over image of delta n plus 1. Okay, now we send kernel to kernel, send boundary to boundary. So if here already quotient to be 0, you send to boundary here. Also in this space, you will get quotient to 0. So it's the right. A question? I think if you can send this image to kernel, also fine, right? Is it fine? Oh, not fine. Oh, not fine because everything inside here should be 0 already. Here you cannot send to something non-trivial here unless you send to 0. Either you send to 0, either you send to something that get set to 0. That to 0. Either you send to 0 or either you send to something is 0. Make more sense? Doesn't make sense. Something that is 0. Something looks like 0. Something behave like 0. Either you send to 0 or you send to something behave like 0. Okay. Okay. But it already sent to something behave like 0 is good enough already. Yeah. So that's what happened in our society. Okay, let's do one more. Let's do one more before we finish. Okay, this one is the boss of today. This is the boss of today. This is super hard. We have quiz. We should have quiz. We have quiz. We have quiz. We have quiz. Okay, so this is super hard. I don't plan to like put out all the glory detail here, but I want you to focus on a few points, and then the glory detail I urge you to check. In particular, Henry will check, right? Henry type this collection. Yeah, I invite you to check, but okay, let's look at what's the statement we want to prove here. So if two continuous map F and G here are homotopy, we want to show that actually they induce the same homomorphism. So you know what it means? So the induced map is the same. But then you need to use that this two map is homotopy. So this two map is homotopy means what? The homotopy occur where? X cross I is an S cross I map. Okay, it's an S cross I. 有很多 chain
变换的。
It's not how you think about this S cross I, but to think about this S cross I, you can think about, for example, so how should I think about this? So let's say you start from some simplex because to talk about chain complex, you need to split your X into n simplexes first, right? So let's say your X simplex has zero simplex. So if cross I, this homotopy will give you a map from a one simplex out to Y. What does this mean? So this homotopy will start from the zero simplex in X and then give you a map from one simplex to Y. So it go up a level, this homotopy. So you need this kind of going up a level map to help you prove that this two is the same. This two map is the same. Does it make sense? Make sense or not? So for example, one simplex in X, right? Cross I, what do you get? Then you get this one. Okay, but this is not simplex yet, but you can split it into simplex. So that means you will have a map from this n simplex here, 2n simplex here, to 2 simplex here, to Y. Make sense or not? Does it make sense? But if you take 3 simplex, cross with I, this is not an n simplex yet, but you can slice it into different n simplex. And this is another map into Y. And somehow this will help you to prove this. Okay, somehow this will help. So what happened is exactly what we discussed just now. So you split your X into n simplex and then study this delta n cross I here. You can chop it into different n simplex. So these are the steps to teach you how to split it. And then we will define this prism operator here. Okay. So why is it prism operator? Because just now you can see that the delta n cross I looks like a prism. Okay. So what does this prism do was you take n simplex in X and then make it into a singular simplex from n plus 1 simplex. Okay, because like what we did just now, we can chop. Okay, we can chop the n simplex cross I into n plus I simplex. Okay, and then we consider this map here. Also, there's some alternating thing happening here. And then what's the thing happening here? I think I need to describe to you. So this VI, this thing, right? This is how we chop up the n+1 simplex. And then what is this F? What is this sigma? I should tell you this. So sigma here actually is just the singular simplex coming from CNX. And then this F is the homotopy. Okay, this F is the homotopy. Okay, it's the homotopy that give you equivalent between F and G. So this F here, okay, maybe I did not here first. So what's this F? This F is coming from X cross I to Y. Okay, so to make sure that this whole thing here is mapping into Y. Okay, this whole thing here is mapping into Y. So that it is a delta n here. So it is a delta n+1 here going to Y. Okay, so this definition is very ad hoc. Maybe it's very ad hoc. Okay, you can check the calculation. The calculation is this. Okay, it's very ad hoc. 知道什么是 ad hoc 吗？就好像莫名其妙 define 出来，然后莫名其妙就有这个东西，很 ad hoc. Okay. And then you can prove this identity here. Okay, there's a geometric identity for this. Okay. You can think of this partial is really the boundary of the prism. Then what is this two here? Because your F right is going between G and H, G and F. So this is the top, this is the bottom. And then if you do boundary and then do P, it's just getting the boundary of the prism without the top and bottom. I urge you to verify this. Very, very magical, but you need to verify a lot of things. Very magical, but you have to verify a lot of things. Yeah, especially the sign. The sign is I don't know how to say. The sign is very scary here. Okay, and then the labeling also. Okay, very scary. Other than the scary part, the nice thing is about this identity here. Okay, so this identity here, what it says is the difference between G and F is differ by this commutative relation here. Okay, let's see how it works. Let's see how it works here. Yeah, so I do some exercise example that maybe you can consider. Okay, so let's see. Let's just use that identity. After this sign hazard, right? We have this identity. Okay, we have this identity here. So yeah, so maybe the identity is this part here. Okay, so we can check on cycle what happens because you want to show that these two map is the same, right? Minus this two map is the same. So what do you need to show? If you want to show that these two map is the same, meaning what? This minus F star minus G star had to be 0 map. Okay, you need to show this. Okay, it is a 0 map. Okay, so why is it a 0 map? So you need to check the kernel sent to where, and then the image sent to where. Everything have to be equal to 0. Okay, so let's check this. So let's say you have a kernel. Okay, you have a kernel of delta n. You put it into this difference here. So what you compute is differ by this commutative property, right? And then on one term, P of delta alpha is 0 because you pick a kernel, you pick a cycle out of it. Then you are an image of something. Okay? But if you are image of something, under that map should be 0. Okay, because you quotient by the image. Okay, and then if you are a boundary, okay, do we need to check that? Macam no need already. Is this the only thing you need to check? Yeah, because if it is quotient by a boundary, then that thing is 0. So 0 go to 0. So the non-trivial thing is actually kernel. Okay, so you already send this the top part to 0, then the bottom part obviously go to 0. Okay, so this is a 0 map. Okay, so a very important property is this. So we extract this idea out. So we extract it out. So meaning if there's a map that satisfies this commutative diagram here, we'll call it a chain map. And then a chain homotopy is something like this. So a chain homotopy between two chain map is a sequence of homomorphisms such that the difference of this map is equal to the commutative property here. So let me draw this out. How should you view this? So C, maybe C2, C1, C0, and so on, and then D2, C1, and then D0. Okay, and then you have F going across, right? F from G to, so F and G is like that. G, F and G, F and G. And then, so we look at F minus G or G minus F. In this case, it's G minus F. Okay, then this GF minus F is equal to this sum of these two map here. So what is this two map here? So Hn is go from a lower degree to a higher degree. So Hn should look like this. H1 in particular, and then H0, and then H2 like that. Okay, and then what is this? So you want this trapezium. This is called a trapezium. So you want G minus F to be equal to Dn. So for example, in this case it's D2. D2 H1 plus H2 D3. Correct? Okay, so for example, in this case here, Gn minus, so in this case G2 minus F2 is equal to D2 on H1 plus what? Plus H2, and then apply addition. Okay, so you should remember this direction. So this map, this vertical map is equal to something that go out and then come back, or you go backward and then come back. Then we will say that there's a chain homotopy in between these two maps here. Okay, you need to take a difference. Then the lemma is a chain map induce homomorphism on homology, and chain homotopy chain maps induce the same homology. So if there are two chain maps that differ by this chain homotopy here, then their induced homomorphism is the same. Okay. Without the prism thing, no prism thing. This is abstract idea already. Yeah, and then not even topological space you need. You just need a chain complex, and then you just need the map between chain complex. And this is the topic of homological algebra. Okay, no topological space, but the motivation is coming from this sign cancelling, cancel, and then you got this equality. But really, what is important is this homotopy equation here, which we call the chain homotopy equation. So if two chain map are homotopic, then you will be differ by this sequence of homomorphism that satisfies some commutative property here. Okay. Yeah. Only got 3 minutes. Speak quiz. Yeah. Actually, what I wanted to do was maybe we don't need to do that. We do an oral test here. Let's do an oral test. 全部人要喊出来，没有喊的话就没有分。Okay, so what's the quiz I want to show here? One is delta complex. One is a CW complex. Okay, and I think of it is I want you to draw torus. I want you to draw RP what? RP2, and then I want you to draw climb border, and then I want you to draw S2. Okay, so let's remove this. Can everyone shout? Shout out your CW complex. Which one is closer now? Maybe delta first. Maybe you got memory first. So what is delta complex for? Maybe torus. Torus first. Remember we compute the homology. What's the picture? Square, right? Okay, and then 一人喊一个很多有箭头要喊，有 orientation 也要喊。上面下面左边右边 ，OK， 上下左右 ，OK。对，这个是 important。This is very important because this is the delta complex. OK， 但是我箭头要怎样放呢？箭头也很重要，这个上去，OK， 上去 ，because you need to make sure your order is transitive Then CW complex 呢 ？Then you CW complex 不用紧嘛，对不对？我不一定要放中间那一横，但是你要放中间一横也OK， 只是你加多一条 one simplex， 这叫 simplex 吗？不是，我们叫做 one cell。对吧 ？one cell 你要加 one cell 也可以，不要加 one cell 也可以，但是 delta complex 一定要。OK，RP2 呢 ？I think 又是 square 吧？square 那个 climb border 也是 square。OK，but the direction，OK， 方向 opposite 要反几个？2个都要反吧？OK， 也要一个 diagonal。这样可以吗？可以吗 ？Then like this. Okay, and then the CW complex again the same. Okay, again the same. Climb border 哪一个 ？Okay, and then 也要加一个中间线，也可以选这个。OK， 不能这个所以怎么办？
往下都不行，
往下就可以。OK，good， 非常好，很好，比我还会就对了。OK， climb border for the bottom， then 你要用一样的也可以，你不要用一样的，就至少都要这一个。OK，S2 S2 怎样？嘿嘿。OK， 很好 ，good。这个就 two cell， so E2 全部 join to a point E0， maybe join at E0 like that， 好吧？delta complex 呢？8个，就是我在班上画的这个，OK， 还有其他方法吗？讲不出画出来啊！你讲不出我给你画。Octahedron tetrahedron octahedron 是怎样？我画不出。8个我不会分那个三角形出来。2个。2个 tetrahedron。OK， 2个 tetrahedron。I think 一个 also can 一个 can 吗？可以啊，怎么不可以哦？怎么不可以？我这样子呢，这样子粘嘛。OK，maybe 这样，and then 这个3个，这一个。Homotopy 或者像 Rachel 讲的 ，take 2 piece of this top and bottom。我有画错吗？没有画错吧 ？tetrahedron 吧 ？Homotopy equivalent。Yeah，I think assignment 不是 assignment，tutorial 有一题是Rachel 讲的，就是这个跟这个。OK， 就这样。Okay, please give me your lecture notes. I will print it out before the exam. Hopefully I can print in color. I must print in color.
有那些图你可以发图，那些都是也可以的。
I will try to print color. Okay. 等一下啊，多欸，没有就用学校的印就好了。